Let's do an example here, median household income. So we're going to be talking about the median in this example, and we don't normally, in this class, we're not really going to do confidence intervals for the median. We'll work with the mean and we'll work with proportions, but whatever, that's all right. According to the American Community Survey, a 95% confidence interval for the population median household income in Texas during the years 09 to 11 is 58,700 to 59,147. What was the point estimate for the study, and what type of sample statistic was it? Well, to be honest, I guess we can't really answer either one of these. We're saying our stats are it's going to be our statistic plus or minus our margin of error. And the margin of error is the same on the top hand side as the bottom hand side the vast majority of the time. In this class, it'll be all the time. So we can assume that the statistic is going to be halfway between these two endpoints then. So basically just take the 58711 plus 59147 and average them out, divide by 2. That should give you the middle number. And then the question is, what type of sample statistic was it? Well, I don't really know what it was. I'm assuming they would probably use the sample median to approximate the population median. But as we learned from the German tanks problem, sometimes we use other estimators. So I'm going to assume it was a sample mean. I'm going to assume it was a sample median. That'd probably be my best guess. And if we just type this in here, Control Enter, 58,929. So my estimate's right in the middle of that interval. What's the margin of error? Well, the margin of error is the number that we add to this number to get this number. So I guess I could subtract these two, or I could take this one minus this one. Or if you just take the difference of these two, that would be two margin of errors, right? You got your stat, then you're going one margin of error above and one margin of error below. So that's a total width of two margins of errors. So I'm just going to go up there and grab that average and take the difference divided by 2. The difference gives me two margin of errors, divide by 2 to give me 1. That's $218. Interpret the confidence interval in the context of the problem. Can't do this enough. I mean, this is, you want to make this just kind of a memorization type of thing, fill in the blanks. We are 95% confident that the interval from blah to blah captures the parameter in context. In this case, captures the true median income of households in Texas. Probably should put the years in there, but oh well. Interpret the confidence level. What does it mean to be 95% confident? Well, that means if many samples of Texas households were selected, the resulting confidence intervals would capture the true median in about 95% of those samples. Just need to practice the wording, understand it, I guess. Calculating confidence intervals. So I already kind of let the cat out of the bag here, but confidence intervals in this class will always be calculated by taking your statistic plus or minus some crit value times the standard deviation of the statistic. And this is actually the formula that is given to you on the formula sheet. Okay, so we just need to figure out what the sensible statistic is, what value to put in here, and what the standard deviation of that statistic is. And this is also going to be on the formula sheet. If you just got to know which one to pick out. So our margin of error then is simply the product of these two things. Okay? Some notes and just thought stuff, I guess. And this really could just be read by you in the notes, but I'll just comment on them and maybe talk a little bit about them. Getting a confidence interval that captures the population parameter the right percentage of the time is very dependent upon knowing the shape of the sampling distribution of the statistic. So we must check the shape every time. So I wrote this a couple years ago, and I'm a little bit embarrassed by it. Well, it is dependent upon the shape, but this kind of seems to imply that that's the most important thing. There's actually 3 checks, if you remember, from our sampling distribution. There's the random check, there's a 10% condition check, and then there's our check for shape, whatever that condition is. It kind of depends on what type of sample, whether it's proportions or means. And we talked about, what happens when these fail. If this one fails, we're fine. If this one fails, we're actually in a better position than you might think. If this one fails, our 95% confidence intervals are actually going to capture like 97% of the time. We're actually going to be more accurate than we would think. Now, if the shape fails, this is true. If the shape fails, we got problems. Our 95% confidence intervals might only capture maybe 90 or 91. I don't know. It depends on how skewed it is and all this other stuff, right? But this is the big check. If this check fails, if you just go out and ask your buddies the question about, whatever else, if you don't take a good random sample, your 95% confidence intervals may only capture like 10% of the time. I mean, who knows? Could be anything. This, by far, is the most important check. This is the second most important. This is kind of meh, whatever. We might talk about that a little bit later. The critical value is tied directly to the confidence level. For 95%, we said it was about 2 standard deviations. For 80%, we're going to have a different multiplier. So this is determined by our confidence level. As you increase your confidence level, the crit value will increase in order to widen the interval so you have a better chance of capturing the parameter. I illustrated that with the applet. The critical value is also linked to the shape of the sampling distribution, as we will see later. So our sampling distributions so far have always been normal. And to be honest, they kind of will stay normal most of the time, but we are going to have some different distributions that we're going to learn a little later, so stay tuned. The standard deviation of the statistic depends upon the sample size, as discussed in previous chapters. For means, it's sigma over square root of n. For proportions, it's pq over the square root of n. In both cases, we have this square root of n factor on the bottom, which means as your sample size increases, your standard deviation decreases, right? Bigger samples, smaller standard deviations, which result in smaller margins of errors. Bigger intervals, smaller margins of errors. There's a trade-off between confidence level and margin of error. To obtain a higher confidence level with a given sample size, the margin of error must increase, and therefore your interval must get larger. If you want to lower the margin of error and make a smaller confidence interval and keep the same sample size, you must lower your confidence level. Whatever, throw that out, that's not that important. So I like this comic, Garfield. Looking at the weather for tomorrow, the high temperature will be between 40 degrees below zero and 200 degrees above zero. And Garfield's got his classic smile and it says, this guy's never wrong. You might say, well, why don't we just calculate 99.999% confidence intervals? Or you might even say 100% confidence interval. And I'd like to talk about this 100% confidence interval, but I don't want to keep going on and on and on forever. Well, I'm going to say it anyway. You use a normal distribution to get your confidence interval. Your z-crits, right? Your cutoffs, if you will. If you want to be 100% confident, then you need to go from negative infinity to positive infinity. So that's like saying the weather tomorrow is going to be somewhere between negative infinity and positive infinity. Okay, there you go. There's your 100% confidence interval. But this is worthless. If you want to be 99.99999% confident, then you're going to get intervals like this. The average IQ is somewhere between 20 and 200. Well, no duh. I mean, you didn't need to collect a sample and do statistics to tell me that. I could have told you that. So we want intervals that are usable, informative, yet also accurate and reliable. You're not going to get, that's why 95 is that golden number. It's kind of the gold standard for a sensible interval. Our methods for calculating confidence intervals are dependent upon the sample being a simple random sample. Okay, so now I guess I addressed this whole thing about the normal. That's the very last thing, as if it wasn't that important. They cover only chance variation due to random sampling. They do not account for the bias that arises from bad sampling techniques. Nothing can fix a bad sample besides throwing it out and getting a good one. Okay? All right, so next section we're going to learn about confidence intervals for proportions and how to actually calculate a confidence interval.